Okay, I guess we'll make a start. The first presentation is by Marius Kocher on honest calibration assessment for binary outcome predictions. Marius is a PhD student, so please devote your time on this presentation.
Okay, so I should have prepared myself with this microphone. I'm sorry that I didn't. Okay, though. Yeah, thank you for introducing me. My name is Marius Puke. I'm a PhD student from the University of Hohenheim in Stuttgart, Germany. And I do present some work on binary outcome predictions and their honest calibration assessment. And this is actually joint work together with Timo Dimitriadis, Lutz Dümken, Alexander Hensi, and Johanna Ziegel. Some of them are here today as well. So I suggest that we directly start with the setup that we face in that project. Essentially, we just have two variables in our word here. So we have a binary outcome, which is denoted by y, and we have a probability prediction for that binary outcome. And you might think of plenty of examples. Very prominent are credit default predictions or outcomes, or what is quite popular in econometric textbooks, where they try to explain logistic regressions using the outcome of a low birth weight. When it comes to assessing this predictions, one often follows the notion of calibration. Calibration in this binary word has quite an intuitive meaning. In a sense, this probability prediction that we issue should mean what it says. So essentially, always when we predict a chance for this event of 5%, then this event should also occur with approximately that frequency. And we can generalize this idea into that formula here. So we define here this function p of x, which is a conditional probability for the event given the forecast. And if this conditional probability equals the forecast itself, then we would be calibrated. And if you think of that formula in terms of that diagram here, that reliability diagram, it becomes even more intuitive. So we plot here this purple line, that's a function p of x, some function, and we can then compare that purple line to that diagonal line. And if these two lines would be equal to each other, then we would be calibrated. And in this case here, you can see that we are essentially not calibrated, but nonetheless, we can learn something from that curve. So what we learn from that curve here is that always when we predict a probability of 50% for that event, that then this event is just materializing with a frequency of 1/3. So this is quite informative, but this function p of x, this calibration curve, is not available, so we have to estimate it. And based on this, one can also think of constructing a calibration test. So if we would test whether this diagonal line or this calibration curve equals this diagonal line, then we would have a calibration test. Such a test is proposed using a very basic way to calculate or to estimate this calibration curve using binning and counting. So what one would do is one would simply bin the forecast values into different groups, and then I can calculate the mean of the outcomes within each of these groups, and then we obtain this black dots here. And what one then can do is one can approximate that curve, and then one can construct a chi-squared calibration test by assessing whether we are significantly different from that straight line. And one tests here for this null of perfect calibration. And this is a famous goodness of fit test proposed by Hosmer and Lemischel some years ago. This is quite standard in the literature, but it has some downsides. So we have the arbitrary choice of the number of bins, And this, of course, can influence the outcome of such a calibration test. And what also can happen is that when we have multiple observation on bin boundaries, then one obtain also some instabilities. This is also known to the literature. Practical work here of Bertoloni and also Hosmer showed that p-values might range up between 1 and 95%, which is quite huge. I want to stress another downside of this method, or of this calibration test with respect to this null hypothesis. So there's one famous sentence of George Box who claimed that all models are wrong, but some are useful. And if all models are wrong, then we can essentially never be perfectly calibrated. But we test under the null of perfect calibration in such a calibration test. This has done some further implications, though. An applied researcher, for example, wish in that setting not to reject this null from a statistical point of view. This would result in quite a nebulous situation. So because we do not really know what is going on, where we do not reject the null. And of course, in large samples, the power of this test converges to unity, and one rejects all the time, basically. So instead of finding the perfect model, we should try to find a useful model. And this is what we try to do by proposing a confidence band for that calibration curve, that function p of x. What would be quite neutral is one can try to come up with an estimate for this calibration curve that is stable. And then one can try to center and calibrate and confidence band around that estimate. And the most neutral estimate for such a calibration curve would be isotonic regression. This would result in this Korp reliability diagram, where we would compare then this stepwise curve, which is this isotonic regression, to the diagonal line. Isotonic regression is neutral because it just makes use of the assumption that we have a monotonicity relationship between the outcomes and the forecasting values. And this is neutral because we would hope that when we predict 10%, that this event is materializing less often compared to the case where we predict 90%. There we would hope that this event is materializing at quite a higher frequency. So this monotonicity assumption is quite neutral in this case, and the benefit of isotonic regression is that it is without any tuning parameters, and we cannot influence the outcome. So as I stated, what would be neutral is to construct somehow a confidence band that is centered around that estimate, but this is quite complicated because we have asymptotic theory that is super complicated. And what people then usually do is bootstrapping, but also these bootstrap for isotonic estimates are inconsistent. So we try to find a different approach to come up with a valid confidence band here. And what we did essentially is we constructed a confidence band just using two assumptions. One, that the outcomes are independent, and second, that this underlying function, that purple line, is increasing. This is what we try to achieve, and therefore we made use of very classical confidence bands, which were proposed by Klopper and Pearson in the 30s of last century. And Klopper and Pearson were proposing an exact confidence band for the case where this underlying function is not increasing, but is constant. And they showed that you can basically express this upper and lower bounds as quantiles of beta distributions. And what we now do is relate their approach to the case where this p is not constant, but it is now increasing. So here we have this increasing function p. And assume for now that we are interested in constructing an upper confidence bound for that value xi. So we fix this value xi, and what one could do is one could simply consider all the data right to xi. So we just use probability predictions that are equal or larger than this fixed value xi. And based on this, we can use this data here on the right to come up with or to construct this Klopper-Pearson confidence upper bound value. Essentially, we can do this for any kind of index interval combination in this area. So for example, we can consider xk to xl, this bluish area, that might result in this bluish highlighted upper bound here. We might use some different index intervals, this greenish or this yellow area here, and we have then different multiple upper bounds, candidate upper bounds. And if we essentially do this for all the possible combinations of index intervals on that range, and if we would have corrected for the significance level for multiple testing in the first place, then we can simply pick the smallest upper value that is arising from that procedure to obtain an upper value for xi. And we can simply do so because we just consider data that is larger than this xi or equal to that xi, and therefore we just get perhaps a little bit more conservative than the necessary, but still valid. Of course, if we would be interested in a lower bound, the same procedure would apply to the left-hand side. So just use the left-hand side of xi to come up with a lower bound estimation for xi. So this is the intuition of those bounds that we are proposing here. And we can give some notion to this here in that formulas. Essentially just this Klopper-Pearson bounds with this algorithm that iterates through all the observations that we have and finds these upper and lower bounds. And essentially, we were able to show that our bounds fulfill some nice coverage requirements here. So we are confident with 1 minus alpha that this underlying function P lies within this confidence bound that we are proposing. So to sum up, we just use two assumption independence outcomes and monotonic relationship between predictions and outcomes to come up with this confidence bounds. This has then some nice or implies some practical implication here. So these bounds that are arising from that procedure are simultaneously valid. That means that they are valid throughout all these x-axes here. These are no pointwise intervals, so simultaneously valid intervals. And this allows us then to essentially test any hypothesis of interest. So we can test this perfect null perfect calibration null hypothesis that I mentioned in the beginning, where we simply check whether this diagonal line is included within that confidence band. Here in this example, we see that's not the case, and therefore we would reject this null. But I claim that this is not very informative. And this was also mentioned in the literature, and there were requests to come up with a different procedure to test for calibration. So our approach also facilitates this. So we are able to test whether the miscalibration is larger than some predefined error epsilon. This epsilon might be small, 10%, 5%, whatever. And then we can also place this null hypothesis. And I will come to this in a minute or so and show how this is constructed. So of course there are some competitor approaches around, as you might imagine, but we outperform these competitor approaches in this binary settings here in terms of flexibility, coverage, and so on and so forth. So we try to apply this confidence bounds that we are constructing here to quite an example. So we use data from the National Center of Health Statistics in the US. They publish each year data on newborn children. For 2017 here, they published 3.8 million births and information according to that. And we constructed this binary variable y, which is low birth weight in this case. And low birth weight is defined as a birth weight with smaller than 2,500 grams. And based on this, we tried to come up with a probit prediction model. We used variables like maternal behaviors like smoking, other diseases, and stuff like this. And what we achieved then in an out-of-sample prediction forecasting exercise, we were able to show with our confidence bounds that this model or the predictions that we were generating here are quite well calibrated. So we see that this diagonal line is captured within this band for all those forecasting values that we have here. Also in this area that might seem a little bit tight at the first place, if we zoom in, we also see that we are capturing here that diagonal line for all the values on the x-axis. So we are kind of able to show that we are well calibrated. And this is what you could do with this procedure. Of course, if your model would not be calibrated, you can simply show that functional form of miscalibration. But I would not do so here in regard of this time constraint. What I want to stress instead is this inverted type of null hypothesis that I was mentioning before. So I claim that our bounds are able to test the null, whether the prediction error, whether the error that we make by predicting x is larger than epsilon. So what you can think of this epsilon is perhaps 10%. So we define this epsilon 10%. And then under the null, we test whether the error that we make by predicting x is larger than this 10%. What we do is we draw then here into this reliability diagram, we would draw here two error lines. These red lines, they both have a slope of 1. The upper one here has an intercept of 10%. The lower one has an intercept of minus 10%. And then we can check whether our confidence band is captured within this lines. And if so, then we would be able to reject this hypothesis that this error that we do by predicting x is larger than this predefined epsilon of 10%. And as this is the case here, we are able to reject that the error that we do make by predicting is larger than this epsilon of 10%. Okay, so let me quickly conclude. So what we are proposing is a simultaneously valid confidence band. So it's a pathwise band, not pointwise, and this allows us to construct these interesting hypotheses that I was mentioning before. And we believe that our approach is quite a sound, statistically sound solution to demonstrate calibration. And it also allows you to assess the functional form of some miscalibration that you might face in your predictions, in your forecasts. And further, we think that this is quite a truthful solution to this criticism of the goodness of fit testing calibration test, to those classical calibration tests, where they have this null of perfect calibration, which we think is not very sensible. And of course, we propose here an almost universally valid approach. So on top of this independence assumption, we also place this assumption of monotonicity between predictions and outcomes. And such procedures always require rather large samples. So we think that we might need at least 10,000 validation observations in our forecasts to come up with an sensibly narrow or tight band. And yeah, this is basically a working paper or the content of a working paper that is available via arXiv. So if you're interested in reading some more stuff onto this work, feel free to refer to it. Or if you're interested in calculating these confidence bands, you might want to check our R package that is hosted via GitHub. Okay, so thank you for your attention.
Questions? One question I had, the diagram with the parallel lines.
Yeah.
If you
that one
kind of squeeze that as you have done there to the point where it's just touching the confidence band.
Yeah.
I think that gives you a statement that you can say with some degree of confidence the probability statement is within
that error.
So
yeah.
You get 2 for the price of 1.
Yeah.
Hypothesis test and the confidence statement.
Yeah, that's correct. Yeah.
Any other comments, questions? Okay, well. Okay,
so thank you again. Try to get this working, but I'm not sure whether you can flip this. This is very cool.
Okay, now let's see if we can find. Okay.
All right. Okay, so the paper is testing for equal predictive accuracy of persistence, and Fabrizio is going to do the presentation.
Thank you very much, and thank you very much for being here. This is joint work with my friend Laura and my former colleague at the University of York. We will be dealing with testing for equal predictive accuracy when there is persistence. So we will take a look at the Diebold and Mariano test when there is persistence. Why do we do this? Well, because I've seen the Diebold-Mariano test mentioned many times in the last 2 days, and so I think it's nice to take another look at it. It's a very popular test, and it's super nice because it has a very nice standard distribution. Diebold called it the only game in town, and I think it was onto something considering the success of the test. And so we said, okay, so let's see what happens when the persistence of the forecast errors increase. This is actually coming out of a puzzle that we ourselves experienced. We were comparing a forecast that we thought was a good forecast against a very bad forecast, a very bad benchmark. And we couldn't reject the null hypothesis. So we sat down and we thought, how's that? What we're going to find out is that as you increase persistence, the size of the Diebold-Mariano test is increasingly distorted. The size adjusted power goes to 0. And the test, after a certain threshold, any answer is entirely spurious. So the test, as we find out, is not reliable exactly in situations in which you compare a good forecast against a very bad one. And that was a bit of a paradox for us. So here is an example. We have the black line, which is the inflation for the euro area from 1999 and all the way on. The blue line is a forecast that you make if you just fit an autoregression of order 1. Not a fantastic model, but just as a pretty example. And the red line is the forecast that you make if you just always play 2%, 2%, 2%. Right. So you look at the top left quarter over there and you think, okay, so the blue model here should win. As you move on, the advantage of the blue model vanishes, but it's still there. Okay, so let's take a brief reminder of the Diebold and Mariano test. First, we all know it. I'm only doing it to establish notation here. So I call dt the distance between the loss function computed for two different predictions, for two different forecasts, forecast 1 and forecast 2, according to any metric of your choice. Although in practice, people seems to prefer the root mean square error, so the mean square error, but any metric of your choice in theory could go. So your dt in the Diebold-Mariano assumption is something that could be seen as a weakly dependent process with a constant mean and ut error term, which is weakly dependent itself, with long-run variance sigma square. So what you want to test here is if mu is 0. So the distance between the two forecast errors is 0. Right. So this is just the inference on the mean statistic. So there you go, you standardize it and it's standard normally distributed. Of course, the catch here is that we don't know sigma square, but hey, we can estimate it. And because it's the long-run variance, the spectral density at 0, what do you do? Well, you take the periodogram, lowest frequencies, you compress it. That seems the most natural estimate. So you stick it in. If you think that the estimate is consistent when the number of bandwidth goes to infinity, then you still have normally distributed statistic. Otherwise, it's t-distributed if you consider the number of bandwidth as fixed. Right, so this is quite standard. The catch is I estimated this long-run variance on the assumption that the process is weakly dependent. What happens if it isn't? We're going to see that if the process is in fact dependent, then we're going to have troubles. So why did Diebold Mariano come up with this story? Well, they said the idea behind the test was if you are thinking of a quadratic loss function, then if you have an efficient forecast, your forecast should be each step ahead should be a moving average of order h-1, right? If you're comparing this with another forecast, maybe not an efficient one, yeah, but come on, we'll be in the same ballpark range. So again, weakly dependent, everything goes through. But in fact, we actually use forecasts, we actually use benchmarks that may not be very close to this moving average h-1. Also, we don't necessarily need to use the square error for the loss function. There could be different loss functions that could generate dependence in the errors, and indeed even asymmetry. So, not necessarily, the assumption there may not necessarily hold. And what we're going to see is that this can be particularly problematic when we look at things over short sample, because if you think, for example, of an autoregression of order 1, and you think the autoregressive parameter 0.9, and you have 1 million observations, well, you can see that the process is weakly dependent. But if you have the same 0.9 and you have 25 observations, then good luck finding out whether that's weakly dependent or it has a unit root. So the length of the sample itself is a problem. Why would you want to use crazy benchmarks? Well, because benchmarks usually are something that we use because they are easy to compute, right? We want to compare a forecast that has been generated, you know, thinking about a very clever model that uses a lot of data. And we want to show that, you know, at the very least, I'm doing better than the next guy who just pulled the number out of the newspaper. So taking crazy benchmarks seems that the least, beating a crazy benchmark seems to be the least requirement that you want your forecast to have. But in fact, the more naive is your benchmark, the more difficult it is to beat it. So let's take a little bit of a look at the theory. So my dt, as I had it before, my distance, I'll write it like mu, and now the error term, I will explicitly, the residual, I will explicitly break it into this yt, for which I assume this rho yt minus 1, and then a ut. The ut is a nice guy, we know, long-run variance omega with the function central limit theorem, so weakly dependent, nicely behaved, all right. But y could possibly have a bit of extra dependency in there. I'm thinking of not necessarily a unit root, but for example, an autoregression of order 1, but you know, with a substantial value for rho. Two models come to mind here, the local to unity and the moderate deviation from the unit root. These are nice models to understand the concept of dependence in a small sample, because basically this parameter rho, when you are very close to 1, it behaves like this 1 plus ct, or when you want to move a little bit further away from it, it may behave like 1 plus the ct to the power alpha, with alpha equal to a number between 0 and 1. So your 0.9 may fall into one of these two categories, or your 0.75, depending on how big is your sample. This automatically gives you an idea of how strong is the dependence compared to the sample of the dimension of your sample. So I have a couple of results that you can derive for the Diebold-Mariano statistic in this case. Results 1 and 2 are one if you think m going to infinity, the other one if you think of m fixed. Really, this basically means result 1 is when you think of taking a relatively large m, a relatively large bandwidth in your experiment. Result 2, when you take m, your bandwidth to be very little, maybe 1. And what you see, if you see result 1, it's neither under the null or under the alternative. So this statistic is always diverging because it's standardized by square root of m. So the statistic itself is always diverging. If you keep m fixed, m equal to 1, the statistic is still, well, it's converging to something which is fairly complicated, but most importantly, the quantiles of this thing are much further away from the quantiles of the normal. So what is m again? M would be the bandwidth that I'm using when I'm estimating the long-run variance with an average periodogram. So the number of periodograms I'm using in the estimate of the long-run variance. Thank you. Right. So this is a terrible result. It basically says that when I'm in that neighborhood, the test cannot tell me yes or no. Whatever, it's always exploding. Right, so then results 3 and 4 move a little bit further away from this very, very close to 1 situation, and it moves to not so close to 1, but still fairly highly correlated. And you get two results, 3 and 4. Now these are organized by this m to the t alpha minus 1 going to 0 or to infinity. And that's a way we can read how big is the bandwidth in this context compared to t. So again, when alpha is very, very close to 0, then I'm in a situation where I still have this divergence, when on the other hand, when alpha is very, very close to 0, then I'm still in a situation similar to the Diebold and Mariano statistic, and the more the persistence goes up, the more I move to the other limit. In the other limit, this guy is actually pushing my statistic again. So again, I would have a divergence there. This tells me that the test may have a little power, because the power here depends on this drift that is of order t to the power 1/2 minus alpha, but not much power, and it tends to diverge anyway. So if you put all the story together, basically the story that comes out is the more you increase the persistence, the more you get close to a situation where you always get a rejection, regardless of whether the null is correct or not. And any power that you could observe is completely spurious. The size-adjusted power will be 0. Right, so I threw some numbers at the computer, and that's what I got. So these are different bandwidths, M1 or T1/4 to 1/3 and so on. And these are different values of rho. So that the default would be to have rho equal to 0. So mu 0 would be the case of size, mu 1 the case of power. The default would be to have mu 0, and there, whoa, pretty size everywhere for any bandwidth. Power, fantastic. As I increase the dependence, 0.5, 0.75, at least for very low bandwidths, still I have decent size. Look at the power, however, it drops. Huh? And right, so the more I go up with the dependence, the more my test is distorted. Bad news. And look at the difference. It's pretty much the same. The number of rejections, regardless of whether I have a drift or not very affected. here I simulated DT, not nice. So here I simulate the errors instead. You get pretty much the same story. So back to my empirical application, I presented the autoregressive autoregression of order 1. It has a very low average forecast error, not much dependence, but my 2% forecast benchmark, on the other hand, very bad forecast, but also big dependence. When I look at a measure of dependence for the loss differential, well, you see that it's heavily persistent, and if I try a unit root test, I don't reject the hypothesis. Now, of course, I don't really think that there is a unit root there, but the unit root test is telling me you are close to having persistence there. So I don't believe any of these long bandwidth results here. That's why I marked them in red. But then if I stick to the low bandwidth, then I have no significance. And so basically, I cannot say that my pretty model beats the benchmark. But that's because I was silly in choosing the benchmark to begin with. So at the end of this story, if I have 1 minute, I don't think that the Diebold-Mariano test is bad. I actually think it's great. The mistake is not in the test, the mistake is with me. Diebold and Mariano, when they wrote the paper, they said, whoever check your data. When they do their empirical exercise, they actually check their data and they check the dependence in their data. All we should be doing is to follow their advice. You know, if you call it the only game in town, well, a game has its rules, follow them, and checking the dependence of the data is the first advice that we should take from Diebold and Mariano. Okay, so that was it. This was fun for us. We understood why our benchmark wasn't working, and we said, yay, our forecasts are good anyway. Thank you.
So we find that you can use the Diebold-Mariano test in this setting, but do you have any idea of what the remedy is? So what can we do instead then?
Well, this is a very, very good question. How do I test for a non-zero mean in this context? Well, at some point, I don't think I can. If I cannot estimate the mean consistently, then goodbye. So there is a range of rho close to 1 where I just don't have a choice. There is a range of rho not so big where I could improve on the format of the Diebold-Mariano test, and Ludes-Giraitis has a very nice different way of handling a test on the mean to cater for the local to for the moderate deviation from a unit root. So it would be a different statistic, not the standard Diebold-Mariano statistic. But you have to know it, that's the point.
Exactly.
So you have to look at the autocorrelations of your data first, because the Diebold-Mariano is the thing to do if the data are not very heavily correlated. However, otherwise Ludas statistic would be nicer, I think. Thank you. Yes, that's what we should say in the paper as well.
Excuse me. First, a comment. I don't think your benchmark is crazy. It's 2% is the target rate for European Central Bank.
Yeah.
And that's
why
a lot of expert forecasters are actually very close to 2%, so it's not that crazy. But my question is, how does COVID affect everything that you did today?
Oh, well, you see, I was dealing with a toy exercise here. So in a way, I was happy not to have COVID in there, because for me, this was an example that illustrates the criticality around the test, more than discussing the forecasting of inflation. For that, I think the autoregression of order 1 is too simplistic. I would want a better model that takes COVID into account after a while, after COVID is observed, I think. And by the way, considering what is happening now, with inflation in the European area. Again, I would have to be more clever than this simple model. But this was, as I said, a toy exercise to illustrate the criticality of the test rather than really an evaluation of the autoregression of order 1 as a valuable forecasting model. Thank you.
Do you have a suggestion how to analyze the sequence if it's dependent or like weakly dependent or not? Like how would you decide on using the normal Diebold-Mariano test or your improvement?
Yes, I think the advice of Diebold and Mariano to look at the correlation of your test statistic is sound, and we should follow it.
So just look at the ACF and look how it...
Possibly. In our experience, we felt the unit root test, we know that the unit root test doesn't have a lot of power. So it will not reject the unit root even when, in fact, rho is 0.9. So in a way, in a crazy way, that was a nice indicator for me of being in the neighborhood. That's what people also do when they do forecasts, and they do pre-testing with the Dicke and Fuller test, and then do the forecast with the unit root model if the hypothesis is not rejected, even when they know that the true value should be below 1.
Thanks.
So let's show our appreciation. Okay, well, this presentation is rather different in that it's looking at the M5 competition and asking, are the conclusions appropriate? So let's start off with a statement by Brad Efron, the well-known statistician, who says basically when they are suitable, pure prediction methods, which include machine learning methods, can be stunningly successful. So the question is, when are they appropriate? And to that we can add not only when are they appropriate, but what are the criteria for measurement that make them appropriate? So an outline of the talk, I'll just very briefly summarize what the M5 competition was about, and we're focusing on prediction intervals. So it's the M5 uncertainty competition, looking at quantiles rather than point forecasts. There are several issues that I'll cover. One, dealing with the basic data analysis. Second, what I've called weight of numbers, and I'll explain that later. And then the question of, are we using the right criteria when we say that this approach is better than that approach? and finally the take-home lessons. So the M5 competition, there's an upcoming paper in the International Journal, so I'll explain it, but basically the data refer to day-to-day sales products for Walmart. It was by state, then by store within a state, category, department, and down to product. So the most granular levels were the product levels, product by state, product by store. 42,000 series, all but 150 of those were at the granular levels, which follow their description referred to as levels 10 to 12. In addition to daily sales, there's additional information available on special holidays, Valentine's Day, etc., and the prices. The analysis used 1900 days for model development and estimation, then 28 days for forecast evaluation. There was heavy input from the computer science brigade, 892 entries in Kaggle, and they were arrayed against 6 statistical benchmarks. The benchmarks did not consider holidays or price data. So what are the conclusions? Well, in the M4 competition, which preceded it, all the top performing methods were combinations of mostly statistical methods. So combinations and statistical methods. Then we moved to M5. Machine learning methods were better than the significantly worse performance of statistical methods. Wait a minute, that's statistical benchmarks. And the substantial improvement of the winning method over the most accurate benchmark. So what changed between these two? Why was statistics great in the first one and booted out in the next one? Well, let's look first at data analysis. First off, there were very long series which enabled the development of machine learning methods. Many statistical projects have very short series and wouldn't be able to accommodate that approach. Despite M4 saying combinations of methods were good, there were no combinations considered in M5. There was no reporting of preliminary data analysis, so there was no consideration of whether holiday effects, special promotions, prices should have been included. They weren't included in the statistical benchmarks. Sales, particularly at the product level, as we've seen in other talks, are often intermittent, but there were no intermittent methods used even on the levels 10 through 12. So the net effect is that the machine learning people, 890 of them, were up against a few benchmarks, and the statistical methods really didn't bring their A game to the competition. So you can comment about performance relative to benchmarks, but certainly not to statistics overall. All right, moving to the next, weight of numbers. You can think of the recent Wimbledon tennis tournament, though, when Serena was number 1, what was the probability Serena would win? She'd win a lot of the time, but not all of the time. If you standardize the idea of number of standard deviations that Serena is better than everybody else, then head to head, she moves 50% on no standard deviations and quickly up the standard normal scale, 3 standard deviations, 0.99 something. But when there are a whole host of other competitors, 127 others at Wimbledon, then you get the lower curve, much lower percentage of winners. Why is that relevant? Well, we have 892 machine learning methods, 6 statistical benchmarks. So you can ask, how did the best benchmark do if they were all equal, just coming out at random? And the answer is the expected rank of the best benchmark is 126. The paper by Makridakis now shows that the best benchmark was 203rd overall. So, yeah, machine learning methods were better, but not by as big a margin as you might expect. And if you focus on the levels 10 through 12, the best benchmark was 41st. So it did better than the 126 you'd expect. So the best design methods are superior for the more complex aggregated series, but the margin of superiority would seem to be less than at the lower levels. What criterion was used? Well, if you think about prediction interval, make it wide enough, you'll always cover the answer, but it'll be so wide as to be useless. Make it too narrow, the observations fall outside. So they created the criterion MSIS, which has a penalty for width and a penalty for missing. If you look at the formula for the upper tail, you can see the width is from the upper point to the forecast, and then if y is bigger than the upper limit, you incur a penalty. Same at the lower level. Add them together, you get the criterion that was used in the paper. Was this appropriate? Well, I'm not going to look at however many thousand series, I'm just going to look at one. But it's one that everybody be familiar with, the Box-Jenkins airline series. As we all know, upward trend, increasing variance. So the classic airline model, integrated moving average, regular and seasonal, and oftentimes a log transform is suggested to account for the increasing variability, though cube root has also been suggested. As an alternative, we considered an autoregressive scheme for the regular element, but retained the moving average for the seasonal integrated moving average. How did this do? Well, in terms of fitting, not want to spend time on the numbers, the alternate model had a slightly lower root mean square error, but it also had an extra parameter, so basically that's a wash. In terms of the holdout sample, 48 observations, in fact, the airline model in the original linear version does better than any of the others, but the logarithmic model is clearly the worst. It substantially overshoots the actual situation. And the airline model generally is slightly better than the alternate model. Moving on, what about the MSIS measures? Well, if you look at the case here, the linear model does better at the lower level, but the alternate model in the cube root version does better at the upper level. So suppose you were planning a new airport. What would matter would be the upper limit. You want to be reasonably confident of accommodating all the customers. And the lower tail really wouldn't concern you. Well, the pictures here show what happens to the different prediction intervals. And you can see, for example, with the logarithmic version, that's top center, the upper limit is way in excess. The actual number of customers in thousands is about 600, and the upper limit is about 1,100. You'd have an airport twice the size of what you needed. And all three of the original airline models are greatly in excess of what you'd want on the upper limit. The alternate model, the limits are very tight. So if you're interested in the upper limit, as you often are for stock planning and a variety of other activities, then the alternate model would be superior. So, quote, it's more important to get the upper quantiles correct, and people will tolerate intervals up to a certain width. Too wide, the intervals lose credibility. So what can we conclude? We choose a forecasting method, the context matters, and the context will lead to the choice of criterion. And typically you're going to have to worry about width versus coverage. And competition results, whether it's the M5 or anything else, are data dependent, criterion dependent, and depend on the strength of the opposition. In this case, we only had the statistics B team playing in the game. For example, it could readily have included combinations of forecasts, certainly possibility of including dummy variables for holidays and so on. So when you look at the competition results, there's a lot of good stuff there, but you need to be critical in your reading of those results. Questions for the future? Well, should we be considering prediction distributions rather than particular intervals and associated loss functions? And typically when we fit a model, we only fit it using criteria for point forecasts, whether that's least squares, maximum likelihood, whatever. Should we have some trade-off between point and interval forecasts in the estimation, such as a combination of mean absolute squared error and the MSIS criteria? And possibly the last word comes from a paper by Januszewski, saying that the difference between machine learning and statistical methods is probably of a tribal nature, which limits the insights into the appropriateness and effectiveness of different methods. So maybe they're not that different after all, and we shouldn't all be jumping on a bandwagon. Thank you.
Thank you for the interesting presentation. Well, you mentioned M4 and M5. Can you make any predictions about M6?
No, it'll depend so much on what criteria they use, and hopefully if I can get Spiros to read this, he'll include at least combinations of methods. There's a long literature showing that combinations work well, and then not to include them in the M5 competition. So hopefully that will be remedied at least.
I have the impression that you're assuming that in the 900 entries, it's only machine learning methods, But do we know if there are what you call A-game statistical methods or combination of machine learning and time series methods in these entries?
Well, you know, I mean, in terms of an A game, I would want, first of all, combinations of methods to consider, but secondly, not just univariate time series, but time series methods that incorporated information about prices and about special holidays. You know, just think of sales of red roses on Valentine's Day. If you miss that, you've got a big error. So moving on from there, obviously a lot of machine learning methods are nonlinear regression based. So I think that's what Janosowski's comment is, that really the difference is more tribal, that we've tended to stick with univariate time series methods when regression is hanging out there. And in some cases, there's strong benefit to going to nonlinear methods as well as linear methods. So we really need to encompass the methodologies of both disciplines.
Sorry, I'm not super familiar with the M5 competition, but am I correct in assuming that people don't know the criterion function that they will be evaluated with when they hand in these forecasts?
It's a good question. I'm not sure what the rules were that were delineated to. I think they'd be able to make a good guess because the MSIS criterion appeared in the literature in 2007, I think it was, right, and is widely used. So my guess is if they didn't know, they could make a shrewd guess.
Right, okay. Sorry, somebody might know the answer?
Yeah, so the measures are unknown, they're publicly available.
Any other questions, comments? Okay, well, please thank the first two speakers.